Let's look at some basic definitions. The first one is the zero vector, 0, 0. It doesn't do a lot for us, and it's represented as nothing or a dot on a page. But it's still important because it forms some of our arithmetic and also proof work. Parallel vectors, two vectors are parallel if they're in the same direction. Now, two vectors are therefore parallel because the only way they can be parallel is if this is vector x and this is vector y. Vector x and vector y are parallel. We write it like this, parallel, only if x is equal to some multiple of y. So basically the direction has to be the same, the length is the only thing that can vary, so we have k some multiple of y. And so we get this rule here. U and v are parallel if u equals kv or v equals ku. And that works. Position vectors, so we've talked about these already, but OA represents a vector that goes from O to A, so it's called a position vector. We've dealt with negative vectors as well, so OA is from O to A, AO is from A to O. They're exactly the same vector but in opposite directions. So that means that negative OA is equal to AO. And you can flip those position vector values around to get that. It's also important to know what a unit vector is. Any vector is a unit vector if it has a length of 1 unit. So we probably need to talk about finding the length as well. So of course if you've got a vector here, so in this case we've got x is equal to 4, 3, and we draw x, which is this vector from there to there, that's x. And because it's 4, 3, that represents a horizontal movement of 4 and a vertical movement of 3. We create this because we're doing horizontal and vertical, we've got a right angle triangle. And so the magnitude of x, which is written as x bar like this, is equal to the square root of 4 squared plus 3 squared. That's just an application of Pythagoras theorem or the distance formula in linear equations, for example. And we get the magnitude, so this is the notation of x, is equal to 5. And so if I go back to this question talking about unit vectors, in this case the magnitude of x is 5. The unit vector in the direction of x, well, x is too long, so the unit vector needs to be cut somewhere down here, so this is 1. If the total length of x is 5, well then the unit vector will be the vector x, but where it's divided by 5. And that's where we get this. So to get the unit vector in the direction of any vector, and the unit vector is denoted x hat, that little hat on top, well x hat is equal to the vector x over the magnitude of x, and that will bring the magnitude down to 1 but maintain the direction. And that's how we do our unit vectors. Okay, and the last thing we need to talk about in this section is the concept of vector geometry. So vector geometry represents using vectors to draw shapes or to represent things on a 2D plane. So for example, if x and y are two non-parallel vectors, then they can combine to make a parallelogram, as we've kind of seen as well. If x and x are equal, that means they're the same length and the same direction, so they're parallel. Y and y are equal, so they're the same length and the same direction, so they're parallel. And we've got a parallelogram, all the properties are met there. We can also use vector geometry though to locate the midpoint of CD and the centre of the parallelogram, and lots of other things as well. So if I zoom in on this, the midpoint of CD is right here, and we can locate that as a vector from A. And that vector from A, here we'll call this vector A. Vector A, let's say we call this M for midpoint. Vector A is equal to AD, whatever that vector is, plus DM, whatever that vector is. Now because it's a midpoint, hopefully you'll see AD is already vector Y, DM is half of vector X. So to get from A to M, or the position of M from location A, is Y plus half X. So we don't know this vector, but we do know this one, and we do know that one, and we can travel in that direction. The other one is the centre. So the centre is there. Of course, the centre is also where the diagonals meet. So in this case, it's about how do we get to that centre. And one way, and there are many ways, but one way of getting to the centre in this light pink pen is to travel along this vector AB and then down into the centre. But that, one of the properties of a parallelogram is that the diagonals bisect each other. So this is, and we'll call this, I can't call it centre because we've already used that, so let's call it P. So we want to know what is vector AP equal to. AP is equal to AB plus BP. So that's all good. We could do, mind you, AD plus DP, or we could even do like AD plus DC plus CP. So try it out. You should get the same thing in every case. AB is easy, that's just X. BP, hopefully because of that, you recognise that because of that property, BP is equal to half of vector BD. And if I have a close look at BD, how do I get from B to D? Well, from B to D is I have to go down to here and along to there. And so hopefully you'll see here that this is now X plus half, and BD is BA plus AD. Now AD is easy, BA not so much. X plus half, BA I'm going to call negative AB, and then AD is just Y, and that gives me X plus half negative X plus Y, and now I can just simplify X plus negative a half X plus half Y, and X plus negative a half X is half X plus half Y. And there we have it. And that kind of makes sense. If we go half X to here, half Y to there, it should take us into the centre. And we're happy with that. So this is a fairly long-winded working, but you can see the structural procedural way that we can approach that question. I'm going to leave that video there, and hopefully it gives you a bit of an insight into the introduction of vectors. All the best.